Yo, what is up, guys? Welcome back. Episode 140 today. Let's go. Another small milestone, 140. Nearly at 150, so that's going to be exciting. I think my first day live streaming is going to be Saturday. I said next Thursday a couple videos ago, but I think what I'm going to do is I'm going to start streaming on Saturday. I was meant to go for a pickleball tournament. But I think it's going to rain and my car's kind of messed up. So I think what I'm going to do is I'm going to stream for the first time at 7 p.m. Central on Saturday, we'll say June 12th. It's Thursday here, June 12th. So Saturday, June 14th. I think I'm going to live stream for the first time at 7 p.m. If you guys haven't already, I literally just created a Discord. So you know, if you guys want to join, you're more than welcome to join. I'll probably post like what I'm going to stream. I'm going to stream definitely at nights every single time. It might not be at 7 p.m. every single day, but probably going to be around 7 p.m. Central Time. So if you guys want to tune in, you know, I'd love to code along with everyone and, you know, do some stuff. I also have a few ideas. I'm going to kind of change up my content a little bit. Still doing the programming every day, but kind of changing it up a little bit, you know, as we progress. I just need to find the time because I'm literally so busy doing stuff. So but I do appreciate all the support, all the comments are awesome. I love when people comment on the videos. It's so nice to see, and you know, it keeps me wanting to keep creating videos, and you know, hopefully it kind of inspires, you know, other people to Leetcode every day. I don't know, you know. So anyway, let's jump into the video. Pokemon 140 today. We got a Kabuto, a fossil Pokemon from memory. Let's take a look at the sound. Kabuto.
Performing on the biggest stage in the world was just one step in.
Don't want to get copy. Here we go. Birdie. 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 That's how sound. Alright, we're gonna jump into some we'll check out our problem of the day really quick. Let's take a look. Minimize the maximum difference of pairs. You're given a 0 index array nums and an integer p. Find p pairs of indices of nums such that the maximum difference amongst the pairs is minimized. Minimize the maximum difference of pairs. Note that for a pair of elements at the index I and j, the difference of this pair is nums I minus j, where x represents the absolute value of x. Return the minimum maximum difference among all p pairs. We define the maximum empty set of 0. We're going to leave this one for now, only because I'm a little confused with the question. I'd rather do something that I understand the question fully. I think that'll be more for probably like a stream sort of question. We have a little bit more time, you know, a couple hours or whatever. So let's jump into our study plan here. Take a look at Leetcode 75. What do we got left to do? This one was a tough question. This one was a tough question. Let's get out of this tree really quick. We've done this before. We were learning trees. Did it on April 13th. Wow, man. I literally thought that was the other day, April 13th. It's literally 2 months ago. A prefix tree is a data structure used to efficiently store and retrieve keys in a data set of strings. Yes, I think I remember. These are various applications of this data structure, such as autocomplete and spell checker. Implement the tree class. Okay. Initializes the tree object. Okay, so would it be like tree is equal to tree. Would it be like this dot tree is equal to tree? Try tree. I don't know how to really pronounce it. Man, this stuff really confuses me. Tries, I don't understand how they work very well, to be honest. Okay, we initialize a tree. Oh, not this. What is it in Python? Oh, shit, dude. I don't remember what it is in Python. I'm blanking out, dude. This keyword, Python. What is it in Python, man? I don't remember. Self. That's what it is. Self.tree is equal to tree. I'm going to take a look at the Leetcode video because I feel like... Oh, whoops. I'm pretty sure he does have a video on it. Yeah, he does. Implement prefix tree try. Blech.
I have to finish writing this paper. I'm swamped.
Just get Grammarly. It's free.
Can it help with what I wrote last night?
Hey everyone, welcome back. And let's write some more neat code today. So today let's solve implement trie, aka a prefix tree. So a trie or a prefix tree is a special type of tree, and it's used to efficiently store strings. The read and search based on prefixes. So let's look at the actual implementation of it. So we're going to have a object. That's what we're going to be doing this time, a trie object. And our job is to fill in 3 functions. The first function is going to be inserting a word into the trie. The second function is going to be searching for a word in the trie to see if the word exists. And the third function is going to be to check if there is a word that starts with a given prefix. So those are the 3 functions we're going to do. And let me just go through the rest of this explanation, and then I'll show you what a trie actually is. So here you can see basically what we're going to actually be doing. They're going to be instantiating the trie, right? We're going to be inserting a word such as apple, right? Then we're going to run search. Does the word apple exist? Well, we just added it, so of course we're going to return true. Apple exists. Then we're going to check, does the word app exist? It does not. The word app does not exist. And third, we're going to try starts with app. Are there any words that start with app? And answer is yes, so we return true. Remember, apple starts with app, so we return true. The prefix, right? This is the prefix. App is the prefix of apple. So now let me show you the actual data structure. So let me show you what a trie is, and in this problem they told us that the limitation is that the words are going to only have characters from lowercase a to z, right? So this is lowercase a to z, so that means we're going to have exactly 26 characters to worry about, right? But so this is a tree, right? It's a prefix tree. It's a special kind of tree. So initially our tree is going to be empty, right? But let's say we want to insert apple. So if we want to insert the word apple, how can we do that? Well, this is what we're going to do. We're going to create a node for the lowercase letter a, right? Then we're going to create another node for the lowercase letter p. And we're going to basically keep doing this for every character in the word that we're inserting, right? We're going to say a, insert it. P insert. We're going to inserted the word apple, right? We can clearly see that. One more thing we have to do to say that this is the word that we inserted is we have to mark the end of the word, right? So this is the end of the word, right? The letter E is the end of the word. So we're going to mark it such that so that this is identified as the end of the word, right? Not, for example, this, right? If we mark this as the end of the word, then we're basically saying we inserted the word AP, but we know we actually did apple, right? Full on apple. This is the last character, so we mark here as the last character. We are marking it even though it's kind of self-explanatory because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe. So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So potentially we could have a node at the first layer for every character, right? So A, B, C, D, etc., right? We could have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with D. So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder node, right? It doesn't have any characters. It's child of the first character that we're looking for, right? So take a look. This is the word we're looking for. Obviously, we're looking for the character A. So we check. Hey, there's the A, lowercase a, right? It's the first character of the word. That's what we're looking for. Great. Now, for this A, we're looking for the next character, right? So does this A have a child P character? It has exactly that. So we do have this P, right? And this is what we're doing, right? We're going character by character in the word we're searching for and checking if a node exists for each character consecutively, right? As a child. So next character, P. Does this have a child P? Yes, it does. Next character, L. We have a child L. Next character, E. This is the last character, so we do have an E over here, right? And last thing that we touch that this is the end of the word. Okay, this is the last character. Is it marked such that this is the end of the word? Is it marked as if it was the end of the word? It's blue, right? That's what we're doing to indicate that it's the end of the word. So it is, right? So clearly we do have apple. We search for apple. What do? We return true because app. This time, let's check if a word app exists inside of our try. And a lowercase a, just like we checked. We do have a lowercase p after that, and we do have a second lowercase p. So since we do have all three of these characters, right, A, P, P, shouldn't this function return true? No, we're not returning true, and the reason is this node is the last character of the word, right, P, and it's not marked blue. Word we know so exist in a function on our tree or a try. If a word starts with app, well, we're basically running the exact same thing what we've done, right? We're starting at the root. We're going to check character by character. So this is pretty, like all three of these functions are pretty similar, right? We're checking character by character for all of them. Start at A exists, check P exists, check another P does exist. So since we found all of the characters, right, we're basically guaranteed that either this is a word itself, which clearly it's not, right? We never inserted app, or we're guaranteed that there is some word below that has been marked, right? Because if we inserted these characters, we only did that because we were inserting a word, so there's guaranteed to be at least something that is marked blue down here, right? So once we found this character, the second P, which is all the characters in here, then we can say true, right there. So if we could just use a hash map for words and search for implementing a try in the first place. Because if we want to insert words and search for words exists, right, to check if a word exists, we could just use a hash map for that, right? Because hash maps can, or hash sets can do both of those things in O of one time, right? But this is really the problem. Starts with, it allows us to check prefixes, right? So now let's say we were inserting another word. Let's say we're inserting the word ape, right? APE. How are we going to do that, right? We're inserting another word. What does that mean? Are we going to say APE and then just create a separate node for each of these as children, right? And just connect them such as that, right? This is a child of A. This is the child of P. Are we going to do that? No, because we could reuse it, right? Why would we have duplicate A's in the first position when we already have an A over here? So if we are inserting this word ape, we're going to leverage this A that we already created. Great. And then we're adding the second character, P. We're going to leverage this P that we already created. And so we've inserted the first two characters. What about the last character, the E? Do we have an E over here? No, right? There's no E in the third position. So what are we going to do? We're going to create another child node, right? Now we create an E, And last but not least, we mark that this is the end of a word. So you can see that a trie actually has the potential to be pretty efficient because we are reusing a lot of nodes. We want to check, does any word start with B? And I'm just illustrating why we're even implementing a trie in the first place. It's because the starts with function is very efficient compared to other data structures. So for example, let's say we had a list was equal to 1,000,000, right? How long would it take for us to check if any word starts with B? Worst case, we would have to check every single word in the list and check if it starts with B. And what if there was 0 words that started with B? Then every time we would have to go through that entire list of 1,000,000 words. But with a trie like we've implemented right now, it's very efficient. Here you can see we have 2 words, right? We have 1 word here and we have a second word here, and it's possible we could have 1,000,000 other words, right? Like clearly there's probably a lot of words that start with the character A and maybe so on. But when we run this function starts with B, all we're checking is we're starting at the root. We're checking, do we have any children with the character B, right? We check this first lowercase, right? For this starts with function, we can return false, and that was done very efficiently, right? 26 is basically big O of 1. So this is a super efficient way to be. All 3 of the functions.
Ryan Miller invests the way he wants to invest. Ryan.
Can't really do that without implementing a trie node. So the first thing I'm going to do is create a trie node, and all we're going to do is just create the constructor. So in Python, that's what I'm doing, and net is basically the constructor. And I'm just going to have a couple of member variables for this. So we are going to have children of a trie node, right? It could have children. It could have 26 children, but instead of doing an array, I'm just going to do a hash map because that's easier. And remember, we can also mark every single node as if it was the end of a word. I'm going to say end of word is going to be a variable. Initially, it's going to be false, but we could set it to true if the character was the end of a word. Notice how we're not actually storing.
Okay, let's make that. Let's try node. We self dot is equal to this self dot. So we close it ends with end of word. Equal to false.
The character itself in the trie node, that's going to be implicit from the.
Oh, we forgot the. Oh man, I'm getting sleepy. Definite.
Hash map from this hash map. So if we were adding let's say a character A, a lowercase character A, we would say to children, we would say children for character A is the key, and we're going to create a new trie node for that character A, right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire trie node class. Now let's actually get into the trie class. So the first thing we're going to do is initialize this. So let's get rid of this comment. And for initializing this, all we're really going to need is a root node, and we can get the rest of the nodes from that root. So we're going to create a root trie node, and that's it. That's all we're going to do for the
Self.root is equal to trie. Okay. Trie node, sorry, that's because that's what I named up here. Whoops. Trie node. These design ones always screw me up too, man. It's frustrating.
The constructor, and once the trie node is created, we basically have an empty tree. Even though we have a root, it's empty because it does not have any children, so we technically have not inserted any words yet. But now let's implement the insert word method. For this method, we are going to have to iterate through every single character in the word. So we're going to initialize our current is going to be set to the root. So we're going to initially start at the root, right? And then we're going to go character by character in the word. And for every single character, we're just going to check two things. Does this character already exist? If it doesn't already exist, so if this character is not in the current nodes dot children hash map, right? So if this character is not in our
Okay, I think I understand this part here. So we get cur is equal to self.root, right? Then we want a loop, right? For node. Okay, let's do for char in word. If char not in cur, is it if char is not in cur? Because cur is the root here, but wouldn't it be like dot children? Yeah, that's what I thought. Cur dot children. Right? Then we add, right? So we add, we go, okay, so cur char is equal to, geez, how would we do this?
hash map
Dot children.
When your kid is hurting and there's nothing you can do about it.
and the key value we're going to use
Cur dot children. The key value we want to use is, well, the current value we're at, right? Or would this be the root?
is the character, and then we're going to create a new trie node. So
Okay. Let me create a new trie node, right? This new trie node obviously has a hash map and an end of word, right, that we can play with, okay? I guess we would need to do an else, right? Otherwise else we would just probably else if there is, we'd probably just want to do, well, we do cur is equal to cur dot children char. I don't know.
So this is as a doing that, skip that shot, move to that character, and then continue.
That's what I did, but I had the else here. Is that gonna matter though? No, it is gonna matter. We don't want the else because then it's not gonna move here. We're just gonna create it, it's not gonna move. So that's why we don't want the else, right? That's our insert right there. Now if we want to search for the word, we would be like, okay, well, cur is equal to self.root. I think we'd start the same way. We go for char in word. Okay, and we would go, okay, well, if char not in cur.children, we would simply return false, right? Else, if it is, we'd want to move, right? Cur is equal to cur.children. Children char. Is that how you would move to the next node? check if last node, right? So we would, okay, well if cur maybe we want to check if last node, we would check probably here, right? If char that means you probably have to keep track of the index too. Range, length, word. If word char not in code.children return false. Cur is equal to code.children word char. Okay, so if char is equal to the length of word minus 1. So if it's the last element, and word char is equal to well, if we got there without returning false, we don't need to check. We just need to be like, okay, is self.children code dot end of word equal to true, then we would return true. Let's see how
you our for loop, right? So we're going to do this for every character in the word, and then by the end of this loop, whether we have to create every node or the nodes already exist for us for this word, right? Let's say it was apple or something, the characters already exist, or we just created them. Now current is set to the last character of the word. So what are we going to do to current? Well, we're going to mark it as the end of a word. So we're going to set end of word equal to true now, and then we don't really have to return anything. So that was pretty simple, right? Not a lot of complex code. We did have to go through every character, and we either created nodes or just iterated through those nodes. And the remaining two functions, search and starts with, are actually going to be very similar to this insert function. So now let's get started on search. So we want to search to root word, and we're going to check exist. Update. Now basically, if the word does exist, that means the entire loop will execute, and then then cur will be the last character of the word, and we know that it is a word if cur has the end of word.
That is such a better way to do it. Such a terrible way. I think my way works, but I'm sure there's maybe something wrong here, but that's right. For char in word, okay, go, well, if char not in cur.children, we return false. Otherwise, we would do cur is equal to cur.children char. We would return char. Cur dot end of word. Yeah.
Variable set to true, so this is the variable we're going to be returning. If this is set to true, that means this is a word and will return true. If it's set to false, that means it's not a word and our function is ultimately going to return false. And now,
okay, I'm pretty confident we can do this one, right? So we would do the same thing here. Cur is equal to self.root. For char in Word, if char not in code.children, we return false. I believe it's the same thing. I remove code is equal to code.children. Char. Code.children char. Otherwise, we would just return false. Otherwise, if it gets out of the loop, we would just return true. I think that should be right.
Now, last but not least, let's get started with the starts with function. And this function is actually going to be the exact same as the search function, except we're not going to have to determine if it's the end of a word or not, right? We're not checking if it is a word, we are just given a prefix, and we just want to know if there's any word that starts with this prefix. So once again, for the third time, we're going to be starting at the root, and we're going to go character by.
All right, I understand it. Last time I did this, I didn't really understand it that well. I don't know how much time I spent on it because it is pretty easy now that I think about it. But yeah, that was a good problem. I'll be back in a second. I'm gonna quickly change my laundry, and we will continue going. Okay, we're back. We're gonna jump into one more problem. Probably most likely a graph problem, I'm thinking. We'll go to our study plan. We're nearly done here, 73. We'll go to our graph theory problem over here. If it will take me in. Word ladder, jump game, O1 matrix. What is O1 matrix? How times n binary matrix map return the distance of the nearest zero for each cell. Oh my gosh, dude. This looks like a pretty straightforward one. It's got 51% acceptance rate. Given m times n matrix mat, return the distance of the nearest zero for each cell. The distance between two cells sharing a common edge is 1. What? What are we returning here, dude? I'm so confused. Map at the highest peak. I don't really understand what is going on here. It's a problem. Explain this problem. I'm confused. Okay, it's popular breakfast. Yeah, we knew that. You're given a matrix map where each cell contains either a 0 or 1. Your task is to return a matrix of the same dimensions where each cell contains the distance to the nearest 0. 0, 0, 0. You want to compute the shortest distance to any 0 for every 1 in the matrix. I'm so confused right now. Multi-source BFS, bro. What is going on here? Task is return a matrix of the same dimension. I'm confused what this means. The distance between two cells sharing a common edge is 1. So these two cells would be 1. All the zeros into a queue and mark the distance as 0. Initialize all 1s as infinite distance or replace all like -1 or infinity. While the queue is not empty, pop a cell for all 4 neighbors up, down, left, and right. Okay, I'm gonna I'm a little confused what multi-source BFS is. I'm a little confused with the problem, and it's kind of pissed me off a little bit. Okay. So I was reading this wrong. So there's only BFS from every one, which would be slow. All zeros at once. Okay, so rows is equal to the length of mat. Cols is equal to the length of mat 0. Okay, we got that. Let's create a directions array. Our directions can be equal to up, down, right, left, right? Our up would be 0, -1. And our down would be 0, 1. Our right would be 0, -1, right? Sorry, our right would be increasing 1, 0. And then -1, 0 for left. Okay. Obviously this is a BFS, so from collections we import our DQ. Okay, nice. We want to create our queue. Q is equal to DQ. Okay. Create our queue. Then we want to loop through for row in rows, for col in cols. If mat row col is equal to 0, we want to add it to our queue. Queue dot append row col. Okay. So why? Oh, we need an array to return, right? So our res can be this is some list comprehension here. We go -1 for something in range. Cols for something in range rows. Creates that res. I always get confused with this comprehension. This pretty much makes everything, makes each cell -1, right? Because reason is, well, we make every 0, 0, every 0, 0, because, I mean, you know, it's, every cell is going to be 0 either way. Others -1 goes to 1. That seems a little confusing here, but I think what we want to do here is we want to go, well, res row col is equal to 0, right? I think the reason why we're doing that here is because then we don't have to do an else. Well, if it's 1, then we do an else statement. I think it's just less code, so, right? Here, now we want to do our BFS, right? So while queue, we want to pop from our thing. So let's pop our row and our col is equal to q.pop left. Okay, so then we can do, well, for new row, new col in directions. We want our new row to be equal to nr plus row new col is equal to NC plus col. If 0 is less than or equal to new row is less than rows, and 0 is less than or equal to new col is less than cols. I believe we're going to need a visited here as well. We didn't make that. We need a visited set. And new row, new col, not in visited. Trying to think here, how would we do this? We check it's in bounds. Well, they don't use a visited array here. Why don't they use a visited? They talk about it. And res new row new col is equal to -1. That means it's not visited. Okay, -1 means not visited. Apparently. Then we make our res new row, new col equal to res row col +1. Q dot append new row, new col. Sorry, Q dot append. Whoops. New row, new col. Obviously need to put double parentheses around here. And we would return our res. I believe this needs a range function because it's not iterable. Okay. We do list comprehension here. We have the queue. We got the row, the col. If it's 0, we make the res row col is equal to 0. Right? Every single 0 in here. Right? We pretty much make it identical. Right? Except this is -1. Right? That's what it looks like. Right? Then we go for row and column. We go for new row, new col. We do, okay, NRNC. We check, okay. If it's 0 and res is equal to -1 means not visited. Doesn't matter, right? Then we come here, right? And we see, okay, well, yeah. Okay, these are two different examples. This is what's confusing me here, dude. Oh my god, dude. Right, so we get to the -1, right? Col +1. I think I'm confusing myself. Can you run through this test case? Like, BFS for me with graphs is like the easiest thing ever. I think I'm just literally confusing myself with the question we want. I think the minus one has confused me because instead we could use a visited set. Yeah, for some reason. So I think what's getting me here is that we're using the -1 here because of the visited, but here we could literally use turn the distance to the nearest 0 for each cell. Well, because it's not 0, it's 1, right? And that's why we do it here, right? So now we go down here and we're looking for return the distance of the nearest 0 for each cell. Here, the nearest 0 is it might be this one, right? Because it's here. The nearest distance, this would be 2. Yeah. I shouldn't even have looked at GPT. I feel like I probably could have easily solved this on my own, but I know I would have. I mean, we pretty much did anyway, but I just was getting so confused with this -1 here. I think when I first originally explained it, it didn't really make sense, but I think it actually does, but I don't know. It's just a placeholder. Again, we probably should use the visited set. I don't really like this. I'm going to leave a comment here the next time I look at this. Used visited set. Yeah, let's submit it. We're going to call it for a day, though. Appreciate you guys watching. And I will see you tomorrow on Friday. Bye-bye.